Hello guys, and welcome back to Introduction to Number Theory. Now I would like to discuss the structure of the solutions of a Pell's equation. Now let me remind you what the Pell's equation is. It's equation of the form x squared minus a times y squared equal to 1, where a is a given non-perfect square number. So let's write that a is not equal to the square, which means that a is not 1, not 4, not 9, and so on. And x and y are unknown integers. And now we would like to understand what is the structure formed by solutions of such an equation. And once again, let us consider particular number a equal to 2. And may I once again assure you that all that will going to happen after this moment is also applicable to a general case, to any a other than squares. So when a is equal to 2, then we have some known solutions. For instance, we know that x equal to 3 and y equal to 2 form a solution, because 9 minus 8 is equal to 1. Let us denote 3 as x1 and 2 as y1. Why did I write these numbers here? Well, the meaning of these numbers is that this is the least possible value of x. Well, if x is equal to 1, then y is equal to 0. It is a trivial solution. It is a non-interesting solution, because now we are speaking about non-trivial solutions. And if x is equal to 2, then y is not integer. So this is the least integer solution of this equation. And corresponding to x1, we have y1, which is the least possible value of y. Let us denote z1 to be equal to x1 plus y1 square root of 2, which is of course the same as if I would have written 3 plus 2 squares of 2. It is a non-integer number, but it is a solution of the Pell's equation in some sense. Well, now let me clarify this sense. We know that we can decompose left-hand side of the Pell's equation into two factors, x minus y square root of a multiplied by x plus y square root of a. And we can refer to these factors as solutions of the Pell's equation, because these are quadratic irrationalities. And if we denote this one by z, then this one is z conjugated. So another form of the Pell's equation is that z multiplied by z conjugated is equal to 1. So this is the form we will be using during our discussion now. Well, we have z1. And z1 is, being greater than 1, is the least solution of the Pell's equation. Well, solution is in this kind of sense. So I can write that 1 multiplied by z1 conjugated is equal to 1, where z1 is exactly 3 plus 2 square root of 2. So let us make a pause for a second and remember that having a non-trivial solution, we can generate infinitely many solutions of the Pell's equation. Do you remember how we can do this? That's right. We can take all this to the power of any arbitrary positive integer power. So let's say k to the power of k to the power of k and also to the power of k, and 1 to the power of k is of course 1, and z to the power of k is not z1, it's another number, it is another quadratic irrationality, which we will denote by zk. So z with number k is z1 to the power of k. Well, we have here z1 conjugated to the power of k. But we know that the operation of multiplication and the operation of conjugation make friends. So we understand that z1 conjugated to the power of k is actually equal to z1 to the power of k conjugated afterwards. So first we raise it to the power of k and then we apply the operation of conjugating. And this is actually zk conjugated. So we have here that zk conjugated and zk actually participate in this equation here. Well, it's not already an equation, it is a kind of a solution of the Pell's equation. So why are we doing this? Well, the main point is that if we take an arbitrary solution presented in the form of quadratic irrationality, like over here, well, some integer plus some integer multiplied by square root of a, well, 2 over here is our value of a. Then, by raising it to the power, we can get infinitely many solutions. And all these solutions form a geometric progression, which I will write down right now. So, z1, which is greater than 1, and then we take it to the power of 2, and then we take it to the power of 3, and then we take it to the power of 4, 5, and so on, and so on. It is an infinite sequence. And this way we have infinitely many solutions. And the question I would like to discuss now is whether these are all solutions of the Pell's equations or not. Well, certainly there are solutions of the Pell's equation that are less than 1. Certainly there are solutions of the Pell's equation that are negative. Well, understanding all that, now I would like to specificate our question. The question is the following. Are there solutions of the Pell's equation greater than 1 other than those written here in this geometric progression? So the proposition is that there are no such solutions. And now I am going to prove this. Well, first of all, let us suppose that there are solutions other than those in the sequence below. So let me write this sequence once more. It's 1, and it's z1, and it's z1 squared, and so on, and so on, and so on, and so on. It is infinite. And let us suppose that there is a solution. Well, let's denote it, I suppose not z, but w, because we don't want to mix it with these solutions. Well, we have another solution. Suppose that we have another solution w, which also belongs to this ring of quadratic integers, and which is also a solution. What does it mean that w is a solution? Well, it means that w multiplied by w conjugated is equal to 1. What does it mean that this is another solution. Well, we suppose that W is a solution greater than 1 other than those that are written, that are contained in this sequence. Well, if W is some other solution, then it must be somewhere between two neighbor elements of this sequence. So we have Z1 to the power of, well, say, L, and it is less than W, and this is less than Z1 to the power L plus 1, and so on. The sequence continues. So we have this sequence, and somewhere between two neighbor elements of the sequence, we have this intruder W. Well, our goal now is to prove that this would lead to a contradiction. So a small question sign. Well, let us begin. The main idea is that if we have two solutions, well, denoted, well, I will use some neutral letters, say P and Q. Well, P, if P is a solution, where by solution we mean a quadratic irrationality, something of this form. So P is something like this, and it is a solution of this very Pell's equation. And also Q, also a quadratic irrationality, also a solution. Then it will be very useful to us to understand that P multiplied by Q is automatically a solution of the very same Pell's equation. It is obviously a quadratic irrationality, and it is also a solution. Well, I don't think I need to write here that all these are solutions. Well, I'll just write that if these are solutions, then from this it follows that PQ is also a solution. Now, take this intruder of ours, W, well, we suppose that it is a solution, and multiply it by another solution. Which one? Well, we can multiply it by Z1 and gain something even more greater than the next element of this sequence. But we can multiply this W by Z1 conjugated, which is over here. And we understand that Z1 conjugated is a number that is actually less than 1. Let me write this down. Well, we understand that Z1 conjugated, being simply 3 minus 2 times square root of 2, it is obvious that it is less than 1. In that case, when we multiply W by Z1 conjugated, we will get a solution. It would be less than W, but what is more important, it will be not here, but here. Let me explain this one. We know that W is between Z1 to the power of L plus 1 and Z1 to the power of L. These two inequalities, when multiplied by Z1 conjugated, which actually means when divided by Z1, because Z1 and Z1 conjugated, they're mutually inverse. So multiplying by 1 means dividing by the other one. Multiplied by Z1 conjugated gives us the following inequalities. Z1 to the power of L minus 1 here we have, well, some solution of Pell's equation, and here we have z1 to the power of L. Well, now notice that multiplying this solution by z1 conjugated brings us to a solution between this one and the previous one elements of this sequence. If we continue this procedure of multiplying an intruder solution by z1 conjugated, then we will receive new solutions between elements of this sequence. Eventually, it will obviously bring us to a solution somewhere over here between 1 and z1. But this is a contradiction because in the beginning we noticed that there are no solutions of the Pell's equation between this one and this number here. So since z1 is the least of the solutions of the Pell's equation, we understand that carrying another solution between them is not possible. So this is a contradiction, which finally proves that there are no other solutions than those who are actually part of this geometric progression. So let me just show that there are no such solutions. Finally, our conclusion is the following. If we take solutions of the Pell's equation that are greater than 1, then they form a geometric progression which starts from the smallest such solution, and then it doesn't end because there are infinitely many solutions of the Pell's equation.